In this video, we look at the simplest example of a asset pricing theorem. This is called the Black-Scholes-Merton model, names of its creators. And this is a model that considers three assets. We have a cash asset that satisfies the ordinary differential equation, or more precisely, its value at time t satisfies the ordinary differential equation dct equal r ct dt, where r is a fixed positive constant. That's for all t in a certain time interval 0t. So we have a time t that is fixed, capital T. We have a stock, that's our second financial assets. It satisfies the stochastic differential equation of a geometric Brownian motion. So dst is of the form mu st dt plus sigma st dbt, and mu and sigma are understood as positive constants. And then our third asset, the one that we're really interested in, the one we're trying to price through the Black-Scholes-Merton model, is what's called a European call option. Okay, so what is a European call option? Well, in words, it is the right, but not the obligation, to buy 1 unit of the stock. So it's a derivative asset. It derives its value from the value of the stock at the final time t, that is agreed upon when you draw the contract, that is the European call option at time 0, for a price that has been agreed upon, k. Okay, so let's turn that into a mathematical equation. Let's call so the cash, let's call that C. T, the process that models the value of cash. St is the process that models the value of the stock. And the European call option, let's denote the price of that as OT. Okay, now the point is that O of capital T, the value of the option at time capital T, we can derive from this description in Word a formula to compute it. So what is the formula to compute it? Well, there are really two possibilities. Either the price of the stock at time t happens to be above k, or it is not above k. So if the price of the stock is above k, then you should be happy to have the call option, because what the call option allows you to do is buy one stock for the price k instead of the market price S of t, which is larger. So if you do exercise your right, if you use your option, you're making st minus k, right? Because you're buying the option for k instead of st, and so you have the difference still in cash. So this is the value of the option at time capital T in the situation where it's a good thing to have the option, because it allows you to buy the stock for a cheaper price than the market price. On the other hand, if st is below k, that is, the market price is cheaper than the price k that you would have to pay if you use your option. So using your option will be silly, and because it's a right and not an obligation, you're just not going to do it. So you're not going to lose any money by having the option, but you're not going to make any money because your option is not worth using. It would just allow you to buy the stock for a price that is above market price. So the value of the option is 0 if, make that not look like a 0, it's 0 if st is less or equal than k. So let's put that in a more condensed form. The value of the option at time t is really the maximum of 0 and st minus k. Okay, now we're going to look at each one of these equations here and discuss how realistic they are in a minute. But first, let me remind you what we're trying to do when we prove an asset pricing theorem. So we're trying to find two processes, A and B, in L2 lock, and define a process which is going to be the replicating portfolio. So a process which value is defined by RT equal A of t times CT plus B of t times ST. So really we're talking about a portfolio that contains A of t units of cash and B of t units of stock, and satisfy two things. First of all, at times capital T, its value is the same as the value of the call option. That is to say that our portfolio is indeed replicating for the call option. And the second thing we're asking from our RT is that it's self-financing, and a self-financing condition which is there to model the fact that no cash or no value should be added or subtracted from RT. The value should only change because the value of cash or the value of the stock is changing. So this is modeled by this equation. dRT equal AT dCT plus BT dST. Right, so in these black boxes we have all of the equations in our model. So the equations, the first three here, this one, and that one, they are the assumptions that we are making, and then this and that will be the conclusion. The conclusion will be we found a replicating and self-financing portfolio. And then we'll use that portfolio to deduce from all of this that the price of the option at time 0 should really be R0. And we'll be able to compute R0 because it will be A0 times C0. And we're going to normalize the value of cash to be 1 unit of cash as value 1. So C0 will be 1 plus B0 times the value of the stock at time 0. Now, before we prove the theorem, that is to say, prove the existence of these processes and such a replicating portfolio, and in fact, do that explicitly, that is to say, find a formula for A and T and B of T such that we can eventually compute the only possible rational price of the European call option at time 0, I want to have a look at each of these equations and try to unpack the assumptions about the model that are made at each step. So question how realistic every one of these equations really is. So let's have a look at the first one. So the first one, dCT equal RCT dt. So this is a compound interest formula. This is quite reasonable, but what is potentially unrealistic in it is that we are assuming that the interest rate is just a fixed number. So this packs a lot of assumption, right? First of all, we are assuming that the interest rate doesn't change over time. We're assuming that it's deterministic, so that we can predict the value of the interest rate exactly all throughout the period. And then on top of that, we're also using the exact same interest rate, irrespective of whether C of t is positive or negative. So if you have a negative value, then you're really looking at borrowing money. And if you have a positive value, you're looking at having money in a saving account that accrues interest, right? As opposed to money that you've borrowed that is accruing debt. Now, usually when you borrow or you lend money, it happens at different rates. So you would imagine that this R here should be really a function of CT that at least takes two different values depending on whether or not CT is positive. So all of these things, making R a function of CT to see the difference at least between borrowing and lending, making R a function of time to allow for changes in interest rate, making R a random variable to allow for uncertainty in the way interest rates evolve over time. All of that is possible and will lead to a more complex model. Now, we're taking this very simple modeling here. This is what Black-Scholes-Merton did, and this is still a very powerful model. But we have to keep in mind that all the assumptions that I just mentioned on interest rate are hidden in that choice of equation. Now, what about the stock? So the stock, well, first of all, we have a a part here, which is some of the trend, which satisfies a very similar equation to what we have for the cash. So all these assumptions that I was mentioning are also somewhat hidden in the idea that this is the way the price of the stock is trending. Now, in terms of the uncertainty that we add to that trend here, we're really adding an uncertainty of the form the relative variation of the price changes as a multiple of the Brownian motion. So this also packs quite a lot of assumptions, because if you think of the Brownian motion, this is a process with normally distributed independent increments. So using this SDE to model the price of the stock includes assumptions such as the relative changes to the price in one period of time are independent to relative changes in the period of time just before it, say. So the fact that the prices jumped up by 20% in one day is not supposed to influence at all whether the price moves up or down the next day. Now, you might say this is unrealistic, and maybe you want to build in some correlation between what happens on different periods of time, but that would require using a different process than the Brownian, something that doesn't have independent increment and that has some built-in correlation structure. Again, we could think about that, but we haven't even developed the stochastic calculus that will allow us to do it. Nevertheless, whenever you write such an equation, you should think about that, about the fact that you've made the relationship linear, so you're looking at basic proportionality, you're using a Brownian, so you have some hidden independence assumptions. Okay, now that on the other hand, and by the way, I should have, that's a capital T here, not a small t, that is perfectly reasonable. It's just the mathematical way of putting this sentence in symbols. Now, that's interesting to look at, not in terms of discussing how realistic our model is, but in terms of discussing how far-reaching our model is. Now, what we would see is that this particular structure of this function doesn't really matter. What matters is that we have a continuous function of the stock price, and it could also be a function of time. So the type of options that we can deal with, as in the original paper of Black-Scholes-Merton, we're looking at the European call option, but we could be looking at all sorts of things as long as we're discussing things that are more generally some function of time and s of t, let's say for a continuous function, then our theory would apply. So this is a very important fact. It tells you what sort of products can you possibly price using this approach, right? So we'll do European call option, we could do put option, that's the right to sell, it's related to the call option, so a simple formula. We could be looking at quite a range of derivative products. It wouldn't change anything to the mathematics. In fact, things go the other way. The mathematicians, we are able to say that at least any continuous function of time and the value of the stock can be used, and therefore, you give me any mathematical formula, I could create a derivative product that matches that formula, even if putting in words what this product does is complicated. So really the question about what sort of things can be priced have nothing to do with the concrete description of them. They just have to do with mathematically what sort of random variable the payoff function, the value of the derivative product at the final time capital T is. Okay, this is about the assumption. What about the goal? So we're trying to find a replicating self-financing portfolio. Now, there's two things to look at here. So first of all, we're trying to find an A and a B in L2 log. I didn't say that I wanted A of t to be positive or B of t to be positive. I didn't put any restrictions on how large they can be. Now, that is to say that in financial terms, that every short or long position is valid. So what we call a short position is as owning a certain amount of something, say cash or stock, and this amount is negative. So if the amount is negative, we say it's a short position in cash, or if this amount, BT, is negative, it's a short position in the stock. And that might feel a little bit counterintuitive that you are allowed to own minus 0.3 stock of something, but you are, right? And at the end of the day, these are just numbers in a spreadsheet, and the market lets you have a portfolio where A of t and B of t can be any real number. Now we'll see that this is important to the mathematics. If we didn't allow that, if we said, you can only own an integer number of stock, or you cannot have a negative amount of anything, although for cash it's pretty clear that you can have a negative amount of cash, right? You can have a debt. But still, if you wanted to make that extra limitation to what markets can do, then the possibility of rational pricing may very well disappear, right? You would have access to far fewer replicating portfolios if you impose more stringent conditions on AT and BT, and therefore the consequence of not allowing certain type of positions would be that, well, you cannot rationally price. So, okay, so this is an assumption that every short and long positions are acceptable, and this is quite a reasonable one in order to reach a result, and that's one we see happening in practice. Okay, well, replicating is what it is. You want the, as a random variable, you want the final value of your replicating portfolio to be exactly the same as the value at the final time of your European call option. Now, last but not least, the self-financing condition. Quite a few assumptions are packed into that SDE. So this SDE is there to prevent something silly. Something silly would be to say, I'm adding cash to the value of my replicating portfolio at some point t, say, or I'm subtracting cash. Now this would be silly because anything could be made to be replicating if you're allowed to do that, right? You could just say, okay, well, I look at the value of whatever it is I want to replicate, say the European call option. I look at the value of whatever portfolio I already have, and then I just bring in or take out the difference in cash, and then they have the same value. Yeah, sure. You can always match any value x from a value y by adding x minus y to y. That's silly. That means that the portfolio is not really on its own replicating. You are replicating by looking at the value and adding the cash. So that's not what a replicating portfolio is supposed to do. It's supposed to be something that you initiate at time zero by getting a certain position, long or short, in cash and in stock, and then you just rebalance that position throughout time, but you don't add value to it or you don't subtract value to it. That doesn't mean that the value is not changing. The value is changing, but the value is only changing through the change of the value of cash, so accrual of interest or accrual of debt, and the change of the value of the stock, which happens according to that SDE, and that's independent of anything you're doing. Right, so this is what the self-financing condition is there for. But when you look at it, you realize, well, hold on a minute. First of all, it's not costing me anything to rebalance the portfolio, so there's no transaction cost. Right? I can get any amount of cash or any amount of stock I want, buy or sell. I can do that instantaneously, and I'm not paying any fees for doing that. So this is hidden in this equation. If we wanted to add something like there is a cost in rebalancing the portfolio, we would need to change the equation to account for that. Now, the other thing is that we are not getting dividends either. You could say, well, if I own a very large number of stock for a very long time, probably I'm going to get some sort of dividends from that. And that should be an increase in my amount of cash that comes from what my number of stock is. Now, we're not taking that into account. So there's all sorts of simplifying assumptions here, and let's write them in blue. So here, for instance, we have a two-way constant interest rate, right? Here we have independent price variations. And here we have, all long and short position allowed. No financial regulations preventing that. And here we have no dividend no transaction cost, no discount either. I mean, you could have something that maybe if you're buying 1,000,000 stocks rather than buying 5, then you pay a bit less. Now, there's none of that, right? You just, if you want 5 million stock, then you pay 5 million times ST, just the same as if you wanted 1 stock, then you just pay ST. So all of these things in blue here are assumptions, actual economic assumptions that are hidden in our choice of equations to describe mathematically what we're dealing with. Okay, so having said all of that, you can look at this Black-Scholes-Merton model in a very critical sort of way. And so this is highly unrealistic. Right? So many of these things in blue are unrealistic. But from a pure mathematical point of view, to start with, this is the simplest situation in which we can prove an asset pricing theorem. So this was historically very important, and it's intellectually very important, because we don't want to try to understand the idea of what a asset pricing theorem is with a lot of layers of added technical difficulties. We'd like to understand it in the simplest case, the simplest non-trivial case possible. Now, you may not have appreciated that all the way through this course, because some parts of this course are quite technical, but nevertheless, this has been a driving principle for me throughout the course. I've always tried to present the theorems to you in their simplest possible form, but no simpler. So, you know, sometimes the simplest form is still very complicated, but I think one should first understand things in their simplest form and then build from that towards more complicated versions. So this is very much what happens with the Black-Scholes-Merton model. It is unrealistic in many ways, but it is not that simplistic that the principle of an asset pricing theorems are not needed. So you see the full concept of asset pricing, rational pricing, and replicating portfolio in action through the proof of that theorem, the existence of the replicating portfolio under the assumptions that we have on this page. Now, that's from the pure math point of view. Now, if you think from the point of view of a practitioner, a simple model sometimes can be very effective. Now, the more complicated your mathematical models, the more parameters you will need to identify. So the harder the statistics become, the more confident you have to be in the data you use to identify the appropriate models. Now, even once you've done your statistical work and you've identified the most appropriate model, you still have to implement that in practice into a computer program. The more complex the model is, the more difficult that is, the more room for error there is, and the more resources, both in terms of time and computing power, you need. So there's really something to be said in practice for using simple models. And indeed, the Black-Scholes-Merton model is used a lot in practice. It works quite well, especially on short period of time and reasonably far away from a financial crisis. In fact, this is used sometimes to predict that a financial crisis is coming, when people start seeing stock prices behave very different, in a very different manner from the geometric Brownian motion used in the Black-Scholes-Merton model. This is sometimes used as an indicator that maybe something funny is happening in the market. So from a pure mathematical point of view, this is a great model because it's as simple as you can make it, yet contains all the ideas of asset pricing theory. And from a practitioner point of view, it's quite a good model because, well, the real world data seems to agree with that model, at least in certain circumstances. Now, on the other hand, as a mathematical modeler, you should be very unhappy with that model because it is clearly unrealistic. It's unrealistic here at the level of interest rate modeling, and you can do a lot better than this ordinary differential equation and be much more subtle about your understanding of interest rate. We might see some of that in the seminar part of the course. And the other part where there really is a lot of room for improvement, even within the theory that we've already developed, is here, right? Having no dividend, no transaction cost, no discount is a little silly. Is self-financing condition that we've expressed with the simple SDE could be refined. It's really quite naive. And again, we might see in the seminar parts of the course ways to refine that. So these are ways to refine our approach really within the stochastic calculus we've already developed. Now, of course, using something else than the Brownian here is also something very interesting, but that takes us on quite a different path in terms of increasing the power of our stochastic calculus. Okay, but this is what the model is. It's a Nobel Prize winning model, and we will derive the solution. So we will prove the corresponding asset pricing theorem. We will construct this replicating portfolio in a minute using the techniques of the course and doing that fully rigorously. Now, I'm going to pause again for just one last remark. If you go back to the original paper, the 1973 paper of Black-Scholes, where they derive the solution and they derive really the formula that's going to give you this value and tell you what the price of the call option should be. They are not doing it with the proof that I'm about to show you. They do it with two proofs that actually are not proofs. I mean, that are mathematically incorrect and haven't really been fixed since then, but that contain the right intuitions. But right now I'm going to show you not the original derivations of Black-Scholes, but a mathematically rigorous version inspired by, but not directly following the argument. Okay, so let's prove Black-Scholes-Merton asset pricing theorem. So I have my replicating portfolio that I'm looking for, and really what I want to find are equations that are going to give me A of t and B of t. So I know that dRt has to be AT dCt plus BT dSt, right? That's the self-financing condition. Okay, but I also know what dCt is and what dSt is in terms of the Brownian motion and a dt, right? So what do I get? I get AT times R times CT times dt plus BT, what is it? Mu st dt plus bt sigma st dbt. So in a more standard process form, or in the form of a standard SDE, this is what we've got from the self-financing condition. Now I'm going to make a wishful assumption. I'm going to assume that our replicating portfolio can be obtained as a function of time and the price of the stock. Well, I know it's true at time capital T, but I'm going to assume that this can be done at every point of time, right? Like in the explicit solutions of SDE that we've studied in the previous chapters. So let's assume that and see what sort of PDE that function f will have to solve. So, okay, let's apply Ito formula. And what do we get? We get that dRt has to be equal to dt ft st dt plus dx ft st dst plus 1/2 dx squared ft st times what we get from the quadratic variation of the process st. And remember that the process st satisfies the equation dst equal, what is it? Mu st dt plus sigma st dbt. So here is the sigma part. So the quadratic variation that I'm picking up is sigma squared times st squared dt. Okay, now let's make that more explicit in terms of functions of dt and functions of dbt. We get dt ft st plus 1/2 sigma squared st squared dx squared ft st. And then we're going to get a st term from the dst. What is the st term coming from the dst? It's a mu st dx ft st. So all of these things are terms in front of dt, and then I have a sigma st dx ft st in front of dbt. So now dRt, I have two different expressions for dRt. Now one way I can guarantee that these two different expressions for dRt match up and therefore find the right AT and the right BT that gives me that, would be to match up coefficients like we did when we solved SDE by hand using the PDE method. So this would be implied by the following. If I have dt ftx plus 1/2 sigma squared x squared dx squared ftx plus mu x dx ftx, or the dt part, equal to the dt part in this expression, which is what? 80, okay, equal to 80 times rct, and r is exponential ERT, and then plus bt mu st, and st is my x variable, so plus mu x, and that's it. So if I have this expression, that will guarantee that the dt terms match up, and to guarantee that the dbt terms match up, I want what? Sigma x dx ftx to be equal to b of t times sigma times x. All right, and I want this to happen for every t in my time interval and for every x in R. Now let's see if we can solve this system of Pde. Okay, so let's have a look at what the system of Pde is telling us. It's telling us that, well, first of all, b of t should be the x derivative of ftx. Again, that's for every t and for every x. That would work if I choose bt in that way. And then I should choose at to be 1 upon r e to the rt times dt ftx plus 1/2 sigma square x squared dx squared ftx plus mu x dx ftx minus mu x, and bt is dx ftx. Which is nice because this cancels with that. Okay, so we have, let's now erase that, we have a formula for AT and for BT in terms of the partial derivatives of f. So if we can find f, we'll certainly have our replicating portfolio. But can we find f? Well, let's remember that our replicating portfolio, RT, had to be of the form AT-CT plus BT-ST. Okay, now we also wanted RT to be a function of T and ST, and it had to be equal to AT times exponential RT plus BT times ST, and I know now what AT and BT have to be, so AT times e to the RT should be 1 upon R times dt ft st plus 1/2 sigma squared st squared dx squared ft st. Okay, and then that's my AT times CT, and then plus BT times ST. BT is dx ft st times st. Now, this would work if we have f satisfying this, and that is exactly a partial differential equation. So if we pick f such that, okay, such that two things happen. First of all, let's multiply all of that by r. R times ftx is equal to dt ftx plus 1/2 sigma square x squared dx squared ftx plus r times dx ftx times xr times that. So if we have this PD for all t and for all x, and we make sure that the final data, so f capital T st, is equal to, or f capital T x is equal to, what was it, maximum of 0 and x minus k. So if we ensure that we have a solution to this partial differential equation matching that final data here, then what do we get? Then we get that RT is replicating, so, and self-financing for AT equal dx of ft, sorry, for BT equal dx of ft is t, and AT equal 1 upon r e to the RT dt ft st plus 1/2 sigma squared st squared dx squared ft st. So, which is just rewriting what I had here. Okay, so what have we done? We've reduced the problem of proving that the asset pricing question has a solution to the problem of finding a solution to that PDE with this particular final data. Right, if I can solve this PDE with this data, then I plug in this value. This is my strategy. You give me the time, the value of time, and the price of the stock at that time. I plug that into my function or the partial derivatives of my functions that I have here, and I know exactly how much cash I need and how much stock I need to replicate the risk structure of my European call option. And in particular, I will have a price for the stock option. So if we have such a solution, we get that the price, the rational price, keyword being rational, the only possible price that we could rationally agree upon of the option is, okay, it's what? It's A0 plus B0 S0. And I have a formula for all of that. So this is equal to 1 upon R times dt F0 S0 plus 1/2 sigma squared S0 squared dx squared F0 S0 plus dx F0 S0 times S0. Okay, so if I got my function f, and of course I've got the data, which is the interest rate and the value, the price of the stock at time 0, then from that I can initialize my replicating portfolio, and I know what the price of the option should be. Okay, so we've reduced everything to solving that PDE. Now, we won't solve the PDE in this video. This is something that can be done in the seminar parts of the course. This is a completely different question from what we've been doing here. It's really a question in partial differential equations. If we stare at that PDE for a second, it's really a PDE that says that the evolution of the function of the time is equal to minus the second derivative of the function on times something in the x variable plus some lower order terms involving only first derivative or no derivative at all. So to a mathematician or a physicist, to people who've done some partial differential equation, this is like a heat equation, except the sign here being, plus on that side, or minus if I put it to the other side, means it's a backwards heat equation. So it's like a heat equation, but with time flowing backwards. And that makes sense because we're really trying to infer information at 0 from information at capital T. So we have here a final data instead of an initial data, and that's because we're looking at a backwards in time equation, for those of you who've done some partial differential equation. Now, exactly how you solve such an equation, we may or may not look at that in the seminar part. That is not fundamentally the techniques of this course. If you were a practitioner and you had managed to reduce your problem to that, you could just plug that into software like Mathematica that would spit out a formula for FTX. But maybe to finish off, I'm going to show you what that formula is. And of course, if I give it to you, you could just do first year calculus and compute the partial derivative and check that this is indeed a solution. We don't have to worry particularly much in here about whether or not this solution is unique. I mean, it is actually, but that's not even the point. As soon as I have a solution like that, I have a replicating a portfolio, and that the value of that portfolio as 0 is the only possible rational price. So let's finish up with this formula. So what we had, by the way, written here, we had written the Black-Scholes SDE, and this PD is called the Black-Scholes Pde. And from the Black-Scholes SDE, you derive the Black-Scholes Pde, and then from the Black-Scholes Pde, you derive the Black-Scholes formula that's exactly going to compute that based on the solution of the equation. So let me show you what the solution of the equation is. So there you have it. This formula right here in the blue box gives you a solution to the Black-Scholes Pde that we have here. You can check that by hand by computing partial derivatives, or you can use some computing algebra software to do that. And the point is that this solution is expressed in terms of the Gaussian integral function, that is to say the function that you obtain by integrating the Gaussian density up to point x. Now, this is a solution. You could prove that this is unique in the appropriate class of solution, and it does satisfy the final data. So you have to realize that, of course, this is ill-defined as little t approaches capital T, because the denominator here goes to 0, but you can compute what the appropriate limit here is, and you will find that indeed you match the final condition. So that's something we will probably do in the seminar part of the course. Look a bit at the theory of such PDEs and check that this is indeed the right solution. But assuming that the PDE work has been done, and now we've checked that this is indeed a solution, then we have a replicating portfolio. Now, the notations in my type notes are a bit different from what I did in that lecture. So B is A and A is B, and we have here just 1, and A is B and B is A. Okay, and that gives you the formula for the price. So this is the very celebrated by people doing pricing of derivative Black-Scholes formula, and you obtain it from the solution of the Black-Scholes Pde that we have here, and that I've given in this blue box by just plugging little t equal to 0 and little x equal to S naught, the price of the stock at time 0. So if you know the price of the stock at time 0, you know the price that you're going to be able to buy the stock for at time t according to the contract. You know, of course, the time t at which the contract will reach maturity. You have your interest rate, you have your volatility rate in the model. Based on all of these data, you have a formula that will compute for you the only possible rational price. So this is the quintessential example of asset pricing. We have SDEs describing the behavior of all our assets. We have a payoff function that describes the derivative products that we want to price. And if we take a PD approach, then we try to get a replicating portfolio as a function of time and the price of the stock. We derive a PD for that from the self-financing condition, and we derive a final condition in that PDE, final data, from the object that we're trying to replicate, from the particular choice of derivative that we're trying to price. We solve the PDE, and then we plug time equals 0 and x equal price of the stock at time 0, and this gives us a pricing formula. So this is a very generic method. It works not just for this particular choice of final data that corresponds to European call option, but for any choice of final data for which the PDE can be solved. And there's a large class of functions here, not just simple functions like that that can be treated. Now, of course, all of that depends on our ability to reduce the problem to a PDE problem. That's why it's sometimes called the PDE pricing method. And we've seen that not all SDEs can be turned into a PDE. This is really dependent here on the fact that the replicating portfolio is just a function of, or its value more precisely, is just a function of t and st. If it was a more complicated process, maybe a process that takes into account the entire history of ST, not just its value precisely at the time t, then this method wouldn't work. And so in pricing something like Asian options or more exotic options that do not just depend on the price of the stock at one particular point of time, but on the whole history of the price, then we cannot just reduce things to a PDE problem. And we have to use a more advanced method of pricing called the Martingale pricing method, which is one of the things that I hope we will discuss in the seminar part of the course. Nevertheless, what you've seen in action right now, so the Black-Scholes model, and that's Nobel Prize winning work and really the foundation of all of the asset pricing methods in mathematical finance, is an application of the SDE theory we've developed so far. So the possibility of solving stochastic differential equation, modeling the behavior of all sort of financial assets using those SDE, and if you want a concrete solution, maybe turning the SDE problem into a PDE problem that you can then solve by whatever method you have at your disposal to solve a PDE problem. Now that concludes the fundamental part of the course. We've seen enough stochastic calculus to do something like that, and we can do it not just for European call options, but for a wide range of derivative products. So we have all the mathematics that underpins this part of finance. Now we're going to move to a seminar part, and we're going to see, now that we have a very solid foundation with all the proofs in this stochastic calculus, we're going to see how we can push it much further, but this time ignoring a lot of the technical difficulties along the way.